Hi everyone. Today I'm going to create a quick demo for you that shows you how to instantiate and utilize the Xilinx Vivado internal logic analyzer, or ILA. The project that I'm going to create is really simple. It's based on the Avnet Minized board, and within Vivado I'm going to instantiate a Zynq core, the ARM Core A9, as well as a little counter, and then the ILA, and then I'll wire up the ILA to the output of the counter. And once we've generated the project, we'll export it from Vivado. We'll then import it over into Vitis. We'll create a quick application so that we can get something actually running on hardware on the Minized board. Then we'll go back to the hardware manager within Vivado, and we'll actually see that we can see that the output of the counter toggling, based on the input clock. And the real strength of this is that on the actual hardware, we can monitor signals inside the FPGA without bringing them actually out to the primary I/O of the device. So it's a great tool to give you internal visibility to all the nodes in your programmable logic fabric. So let's go ahead and get started. First thing I'll do is create a new project. Wow, this is special. There we go. And let's build this in the right place. And we'll call this the ILA Demo. And we'll go ahead and pick RTL as the project type. Since Vivado is board aware, I'm going to select the boards, go to the vendors, click on the down arrow, and we'll choose Avnet. There's my Minized board. Go ahead and click next. I'll finish. And as we're going through this demo, if I'm at a part in the process where the processor of my PC is just chugging away and there's nothing going on, I'm going to edit out those parts of the video just because it's a waste of a file, and these files become really large. And it's a waste of your time just because you're going to be sitting there watching this machine chug away and there's no additional value for you to be watching that. So I hope you're okay with that, and we'll proceed here. So here we are in the project manager. Under the IP creator, I'm going to tell it to create the block diagram. I'm fine using the default values here. Click OK. All right, so here we are with our diagram editor. I'm going to go ahead and click on the plus sign. First thing I'm going to add is the ARM core. So if I just type in Zynq for the Zynq processing system, that's going to bring that up. I'll double click on it. That will add that IP block to my diagram. I'm going to go ahead and run the block automation. I'm fine with all the settings that it's recommended. Click OK. Now I'm going to go ahead and add my counter. So add IP. There's my binary counter. Left click on it. Alright, so I need a clock and I need to do something with my outputs. I'm going to go ahead and double click on this block. So I want to cut that down to 8 bits just because. And we'll make this 8. That's fine. I'm going to go over here and add a 10 megahertz clock to the Zynq processing system fabric, and that's what I'm going to use to clock my binary counter. So I'm going to double click on the block, go over here to my clock configuration, my fabric clocks will enable clock 2, and we'll set that up for 10 megahertz. Say OK. So now I can wire that up. So I left click on that port on my processing system, drag it over to my counter. I'm going to go ahead and have it automatically do the layout of the blocks. That's a little bit neater. The next thing I'm going to do is I'm going to add my ILA. So left click on the plus sign, ILA. There's my integrated logic analyzer. Double click that. Okay, so I'm going to double click that to configure it. I don't want to use this to monitor the AXI. I want to use it to monitor some native signals. And how many ports do I have? I have one. How wide is it? It is 8 bits. So we'll click OK. Now I'm going to wire that up from here to there to F clock 0 of the Zynq processing system. Let's see what speed that's set up for. I want that to be at least 50 megahertz. You have to make sure that the clock for the ILA is faster than the JTAG clock for your programmer. I think my programmer is set for 40 megahertz, so if I set this for 50 megahertz, that should be plenty. And I'm going to set both of these for 50. Okay, the next thing I need to do now is to tie the inputs of my ILA to the outputs of my counter. So I'll put my mouse on the outputs of that counter, drag it over here to the ILA. It makes that connection for me. I'm going to lay out automatically. That looks good. The next thing I'm going to do is I'm going to come up here and I'm going to validate the design. So if I left click on that little icon, validation successful. All right, so the next step in the process is to generate an HDL wrapper. So I have to generate an HDL wrapper for this block diagram because the synthesis tool wants to see that as its input. So let's go over here to our sources tab. We'll select it by left clicking on it. Here's my block diagram, design_1.bd. I'm going to go ahead and right click on that. Right here I see an entry in my pop-up window for create HDL wrapper. So let's left click on that. We'll let Vivado manage the updates. What that's going to do is it's just going to create an HDL net list that instantiates all of the blocks that I've specified in my block diagram. So it'll just be a textual representation of that block diagram. All right, so here's my HDL wrapper. So design1_wrapper.vhd. So that tells me that it's a VHDL file. Okay, the next thing I got to do is I got to generate the output product. So these are the other files that the synthesis tool will need. So I'm going to go ahead and right click again on that file name. And here's my pop-up window, and there's generate output product. So I'll left click on that. We'll go ahead and use these default settings, and we will generate. All right, so we're done with that. The next thing I'm going to do is I'm going to go ahead and just jump right to the generate bitstream. Now the tool is smart enough to know that if you haven't already created all the steps or completed all the steps required to generate the bitstream, it will pick up wherever it needs to and execute those steps. So I'm going to go ahead and click on Generate Bitstream. Okay, so it's telling me there's no implementation available. So the tool went ahead and did the synthesis run. And the synthesis run is where it takes all the files that we generated from generating output products and the wrapper, and it generates a big flat VHDL netlist with generic Xilinx primitives. What the implementation phase is going to do is it's going to take that um, netlist of generic Xilinx primitives and map it into the actual primitives that are available for the specific part that you have chosen when you created this design. It's also going to do all the place and route um, and the I/O assignment and all that kind of stuff based on your design constraints. So let's go ahead and let the tool automatically run the implementation and then the generation of the bitstream. Okay, so we've completed the implementation and the generate bitstream. I'm going to go ahead and export that file now. So I go to the file pull down, select export, and then export hardware. Leave the default there. We're going to include the bitstream. And I'm going to go ahead and leave the default file name and the location. All right, so that completes the writing out of the bitstream. Okay, now that we've successfully exported that design file, we can go ahead and open up the Vitis tool. To get to Vitis, we go to the Tools pull down, left click. We move down to the Launch Vitis IDE entry and select that. That's the correct workspace, so I don't need to navigate to a new one. And we'll go ahead and click on Launch. And here we are in Vitis. So let's go ahead and go to the File pull down, New, and we're going to create a new platform project. And when we create a new platform project, we're going to input that file that we just exported. Then we're going to create all of the files necessary for the application development tool to be able to create applications based on that hardware that we just defined in Vivado. So it needs to, the tool needs to understand all the IP that we instantiated, like that ARM core, as well as any peripherals that we're using. And the platform project will create all of the include files that are necessary to exploit all of those resources that we just specified. So I'm going to name this the Minized platform for ILA. And I'm going to have to browse to where that XSA file is. And here it is. Notice for operating system, we're running in standalone. We could have chosen the free RTOS or Linux, but this is going to be a bare metal project. And then our processor is the Processing System 7 Cortex A9. So we'll go ahead and click on Finish. All right. So one of the things that the Vitis tool allows you to do is it allows you to develop firmware from a higher level. And what I mean by that is if you want to use the UART, for example, you don't have to know what the register address is for setting the baud rate, or you don't have to know what the register address is for loading the transmit register. You can use things like standard I/O and just do a print to the standard I/O device. Now by default, the tool wants UART 0 to be standard I/O. Now the way that this board was designed, the UART that's actually tied to the UART to USB bridge is UART 1. So what we need to do is we need to change the board support package so that it specifies UART1 as standard I/O, so that when we write out hello world, um, we'll get the data going to the right UART. So I'm going to click on the board support package here, and then I'm going to modify the board support package settings. We'll go to the standalone. Here's standard in and standard out. I'm going to go ahead and assign both of those to UART1. So for using the ILA, we don't really have to do this, but it's just, I like being able to look at the console terminal and see that string come out that lets me know, okay, that processor is up and running. Everything is doing what I anticipate that it should. Okay, so that's been modified. So to compile this platform project, I'm going to right click on it, and I'm going to move right down here to build project. So that build is complete. And everything looks good. So the next thing we want to do is actually develop the application that executes the hello world. And we just need to do this because we need that clock that's coming out of that processor block. So we'll go ahead and write the application to send out hello world. That will fire up that Cortex ARM core, um, and then we'll have our clock, and we can go ahead and look at the output of that counter using the ILA. So to generate that application, we go to that file pull down again, left click on it, new, select application project, go to next, and we've got our Minized platform, so that's the correct board support package for this project. Click on next. We'll call this Hello World Minized platform. And that's just an arbitrary name. It doesn't really have to be tied directly to the name of the board support package. And we'll click on next. And that looks good. We'll click on next again. It's going to pull up the different templates, including the one for Hello World. I'm going to go ahead and use that one. You see there's other templates that I could have chosen. And then I'll click on Finish. And there we have it. So now what I need to do is compile that application, and this is the application that's actually going to run on that ARM core. So I'll right click on it, move down to build project, left click on that. All right, and the build is complete. So we are ready to run here. My board is plugged in. I'm going to go ahead and right click on Hello World application and start up the debugger. So we'll select launch hardware. So it's just programmed the memory attached to that Zynq device. All right, now I'm going to set a breakpoint here, right where this cleanup platform is, because I don't want the code to do anything to stop that processor. Also, just so that I can verify that the processor is running, I'm going to go over here to the serial terminal, click on the plus sign to configure it, and I'm going to select port 4 because I know that's the one that's tied to that USB to serial bridge. Click on OK. And we're ready to run over here. So if I push the play button, left click on that, we can see Hello World. So I know that I've programmed that device correctly, it's up and running, and it's just sent a couple of strings out of the serial port. So now to see the ILA in action, I'm going to go back to Vivado, down over here in the Flow Navigator to the Hardware Manager. So left click on Open Hardware Manager. All right, it says right now no target is open, so let's go ahead and left click on that. Auto connect. So if I look over here, I can see all my counter bits in the waveform viewer. If I go ahead and click on this little run button, we've triggered the ILA. So now if I go over here, I can see that there has been some kind of activity here. I'm going to zoom in, and we can see here that in fact that counter is counting like it's supposed to. B9 is followed by BA, BB, BC, BD. So that integrated logic analyzer is connected to the output of that counter that's running at its full speed, and it's extracting that data and it's sending it up to the PC and it's displaying it in this waveform window. So this is a really powerful debug feature. Any of your signals in your design, you can connect up to IP blocks, and you can monitor, what's going on inside that device without having to actually assign those signals to output pins and then hook them up to a logic analyzer in your system, which can be a real bear when you've got devices with, hundreds of I/O pins that are fine pitch in a BGA. So it's a really powerful feature that they have here. Now, one thing to keep in mind is the ILA and the buffer memory where it stores this information are implemented from the same pool of resources that you're using to implement functionality inside that Zynq device. So the more memory and the more of the lookup tables and all the other programmable logic that you're using, the more that you use for your application, the less is available for the integrated logic analyzer. And vice versa. If you want a really nice deep trace buffer for your logic analyzer, there's going to be less memory available for other features. So it's a little trade-off that you have, but having this capability in there is a really powerful feature that they've added to the Vivado tools. So I hope you guys have found this helpful. If you have any questions or comments, please feel free to leave them, and look forward to creating other videos. And if there's other topics that you'd like me to cover, please let me know about that as well. All right, thank you very much for watching. Bye-bye.